Okay guys, what I'd like to do today is throw a little example at you that I think ties together work, power, and energy in a practical Wyoming sort of way using archery. So just to set it up guys, and I don't know, my drawing's a little shaky, but he has a recurve bow. The arrow is going to be launched perfectly horizontal from 1.5 meters above the ground. And the draw length that this person has is about 0.8 meters. The average force required to draw the bow is about 300 newtons. So if you put a scale on the string and you pulled back on the string, you would get 300 newtons on average as you pulled it back. Okay. The draw time is about 1.2 seconds. The mass of the arrow is 70 grams with the arrowhead and everything on it. And the bow firing time, and I kind of came up with this theoretically, bows fire pretty quickly, and so they get that work done almost instantaneously, and so we'll see that the power goes up later on. So just to kind of give us a thing to kind of shoot for at the very end, what I did is I said find the work required for the ground to stop the arrow. We're going to assume the ground is perfectly horizontal. The arrow is going to fly out and stick right in the ground. And when it sticks in the ground, we're going to figure out how much work the ground did to stop the arrow. Does that kind of make sense? That's where we're heading eventually. In order to get there, we're going to do a couple preliminary steps. And guys, when you go to draw the bow backwards, and you draw to your draw length, you are going to pull with a force for a distance. You are doing work on that bow string, and that work would be equal to the force times the distance, which comes out to be 240 joules. So by drawing that bow back, you did 240 joules of work, which should, because of this is the work energy theorem, the amount of work you do changes the energy. In this case, we're storing up potential energy. So we did that much work, so that therefore we have that much potential energy stored in the bow, ready to be converted into what? Kinetic energy. So upon release, the potential energy is converted to kinetic, and guys, we can use that to find the initial velocity of our arrow coming out of our bow. And guys, early on in bow technology, before they had a thing called a chronograph, a chronograph is just basically two lasers that sit like this and you shoot through, and it times when the arrow triggers it here and triggers it there. You know the distance they are apart. And if you know the time and distance, you can come up with average velocity. Okay, that's kind of a newer technology way to find the velocity. But this was one of the ways you could do it. You could measure the work put into drawing the bow, and then, assuming no friction, you could kind of get a maximum velocity calculation of the arrow coming out of the bow. So we say 240 equals 1/2 m, which is the mass of the arrow, 0.07, times v squared. You come up with initial velocity of 82.81 meters per second squared, which if we go to miles per hour, we have to go a little bit more than double. So we're looking at probably like 190 miles an hour. Okay, and then we could take that to feet per second. What's that times 3? Is that like 250 feet per second? Okay, which is a pretty fast bow for a recurve type bow. In fact, it's really fast. Okay. Once we know the velocity of the arrow, that's going to be the initial velocity of the arrow in the which direction? In the x direction. Now, because he's 1.5 meters above the ground, is the arrow going to have some y velocity because of gravity pulling it down? Which we've done this so many times, guys. We have the kinematic equation. We solve for velocity in the y direction, which is a really small component comparative to the 82.81. We plug it in here, vx squared plus vy squared, square root, to come up with not our velocity in the x and not the velocity in the y, but the total velocity. And we've done that enough times that I don't have to spend much time there, right? Does that make sense to everybody? Okay. Once we know the velocity, that's the velocity that the arrow is going to have right when it comes down and strikes the ground, right? Are you with me? Now this is the big leap, and this is where kids kind of struggle on tests and on problems, is making this leap. We did work to store energy in the bow. And then when I let go, the bow did work on the arrow to convert potential energy into kinetic energy. And a lot of kids, when we get to this last step, find the work required to stop the bow or stop the arrow, they're always thinking work equals force times distance. And that's not what we want to look at here. Work also equals what? Change in energy. So the arrow had kinetic energy. Once it sticks in the ground, it's not going to have any kinetic energy. And so did the ground change its energy? And so in order to find the amount of work that the ground does, we say the work is equal to the change in energy. In this case, it's the change in kinetic energy. So we say 1/2 mv squared. We plug in our mass and our new velocity with the y component factored in. And the ground is actually going to have to do a little bit more work to stop the arrow than the arrow did to get the arrow moving. I'm sorry, the bow did to get the arrow moving, because gravity has done some work on it and increased its energy. Does that make sense? Okay. Now, in the real world, guys, would we have air resistance and frictional type issues that would probably diminish the arrow's energy? In that case, though, we could go into what we call, remember, the principle of conservation of energy. We can never create energy, we can never destroy energy, we can only convert it from one form into another. And if we got into that realm where we had friction, then we'd be not losing, but we'd be converting energy into stuff that really wasn't useful, called what? Well, heat, right? Friction leads to heat, and we'd be losing some of our effective, useful energy to heat. Make sense? Okay. So guys, that answers our initial question. And then here at the end, just to throw in some power stuff so you guys get a chance to see that. Power is basically how fast you do work. Okay? Velocity was how fast your position was changing. Acceleration was how fast your velocity was changing with time. Power is just simply how fast you're doing work, or how much your work is varying with time. And so if we look here, the power used to draw the bow back is work divided by time. We did 240 joules of work to pull the bow back. If we did that in 1.2 seconds, the amount of power in that was 200 watts of power. Okay, we did work pretty slowly. Now, if we talk about how much power exerted by the bow string on the arrow, then that goes way up, because the bow does that how? In a really, really short period of time, or it does it very quickly. And so if you'll notice, it did the same amount of work, but it did it in what? A lot less time, okay? Which leads to 48,000 watts of power, okay? So in your mind right now, I want you to just be thinking of work, as power as kind of how fast work is done. Thank you.